Welcome to our 5th unit called Orbital Hybridization. To explain molecular geometries along with orbitals, we often assume that the actual orbitals on an atom, typically we're referring to those around the central atom, are actually going to mix and form new orbitals, typically called hybrid orbitals. So we've defined orbitals as different shapes that electrons can be found in different areas, but now we're saying the molecules overall have this overall shape, and that gets a little complex. So we say they'll mix, form hybrid orbitals. The process of mixing atomic orbitals is called hybridization. We just had to make sure that the same number of orbitals that are occupied stay the same. Now this really isn't all that big of an issue. That's just kind of a key requirement to properly hybridize something. Now if you just follow the instructions I'm giving you, that is actually always ensured. Just in case you ever ask, make sure the orbitals stay the same. The types of hybrid orbitals that form are determined by the electron geometry of the atom. And that is determined again by how many bonding and non-bonding pairs there are. Again, we typically call those electron domains. So our hybridization is defined as the electron domains, which means that we don't count double bonds as multiple domains, if you will. So if we had an atom where carbon, a lone pair, that is 3 domains, not 4. That's our main reminder. So we'd have 1, 2, 3. And this chart below represents what type of hybrid orbitals will form with the corresponding number of electron domains. Now, if you'd like a better picture of this, there are many in your book. Basically, it's a little bit hard to describe, but this, if there are 2 electron domains, basically the outer s and p orbitals are going to start mixing. We have s and p2, then we've got 2p orbitals that are kind of sort of mixing. Like I said, it's a little bit weird. Feel free to look it up, but I'm not going to go into that. What you need to know is that if there are 4 domains, we're going to have what's called an sp3 hybridization. Or if there's 6, it's called sp3d2. That represents we have 1 s orbital, 3 p orbitals, and 2 d orbitals. Now keep in mind that we typically have, this isn't saying 2p and 3p mix. Whenever we can hold 6 electrons in p orbitals because they come 3 at a time. And we can hold 10 in d because they come 5 at a time. This is representing 3 out of those 3 p orbitals are going to overlap, and 2 out of those 5 d orbitals are going to overlap. That's what we're referring to, not how many different energy levels or subshells will be mixing. Now this following phrase has actually helped me learn this. I learned this when I was in high school, got this from my mom. It works. And it's basically sp23d2. Now, let me remind you what the actual order of the hybridization looks like. There you go. If you remember that every new level of hybridization is building on the previous one, then this helps. So our first one is sp. Then we added 2. Then we changed that to a 3. Then we added d. And then we put a 2. So sp2, 3, d2. Now if you'd like to memorize them in order, it's fine. Go ahead. Like I said, this just helped me in the past, so hopefully it helps you. So, sorry it's off in the corner, but that's to give us space to write. Describe the hybridization that occurs on the central atoms in the following molecules. Using that chart I just showed you, the sp23d2. Pause this for a bit, come back with answers to those hybridizations, and I'll show you how you do them. Alright, here's a hybridization. You may not have known, and if not, I'm glad you're learning. But boron actually only really wants 6. So in this case, we don't actually need 2 other electrons. To be honest, I'm not really sure why. It's just boron's fine with 6. So then we have sp2. That's sp2. Water is sp23. sp3. sp2, 3, sp3, sp2, 3, d2. There you go. That's orbital hybridization. Thanks for watching.